Hi, I'm Shenghao. Today I will talk about our work on Unmasking transformer, which studies the inverse attack on the training data given the weights inside the transformer architecture. Since the release of ChatGPT, the world has witnessed the outstanding performance of the large language models on human-like tasks such as machine translation and creative writing. The success of the large models is because of its use of the attention scheme, which enables the machine to prioritize certain inputs by the self-attention scores, allowing the so-called in-context learning. Here we present the canonical definition of softmax attention, which is studied by our algorithm model. Uh, Impressed by the ability of the transformer, researchers are concerned about data security and privacy when training large models. Therefore, we are asking this natural question. Is it possible to recover the input data by analyzing the attention weights and model outputs? Driven by this concern, we propose a regression model shown on this slide, which is an inverse problem that searches for an optimal matrix X, which represents the training data, that minimizes the Frobenius loss. Here, in this model, W represents the matrix multiplication of key and query, V represents the value matrix, and B represents the output. This slide displays a graph of our model construction for you to better understand it. We are applying a quite straightforward analysis method to our optimization. First, we directly calculate its Hessian. Then we prove some good properties such as Lipschitz continuity and positive semi-definiteness under some mild assumptions. Last, we are able to apply a suitable Hessian-based algorithm to solve the optimal problem. Now let me introduce each set. Due to the complex formulation of our model, we use auxiliary functions to simplify our calculation. As shown on this slide, we represent the loss as the summation of the loss at each entry, denoted by Cxij, which is given by the inner product of the softmax probability vector of the ith token, denoted by Fxi, and the value vector of the jth token, denoted by Hxj, and they subtract the corresponding entry of the matrix B. Basically, in our calculation, we first derive the gradients and Hessians for simpler functions, and then we combine them by the chain rule to give a final result of the loss function Lx. Now we consider the Hessian of the one-unit loss function Cx of the I0's token and the J0's token. Here we are taking the derivative of Cx with respect to the vectorized version of matrix X, which means that our Hessian is defined by a ND by ND matrix, with its I1 J1, I2 J2's entry being the second order derivative on the I1 J1's entry of X and the I2 J2's entry of X. And of course, this is the vectorized version of X. I will show you a graph on the next page to help you understand. By our construction of the problem, we notice that when the indexes such as I0 and I1 are different, some terms of the derivative will disappear. So it will be more efficient to for our verification to split the Hessian into different cases. However, the general formula of the Hessian does not vary by the index j, but it does depend on the index I. So we only classify the Hessian by the relationship of I0, I1, and I2. For example, our first case is when I0 equals to I1 equals to I2. And our second case is when I0 equals to I1, but does not equal to I2, and so on. So in each case, we define a D by D matrix, H1, I1, I2, or H2, I1, I2, to represent the partition of the Hessian with coordinates I1, I2. Here, this graph shows the partition Hessian. So we are writing the Hessian as a n by n matrix, where each entry is a D by D matrix, classified as in the last slide. We only have one type 1 at I0's entry, and we have n minus 1 type 2s on the I0's row. We have n minus 1 type 3s on the I0's column. We have n minus 1 type 4s on the diagonal, and all other entries are of type 5. The reason why we do this is that the formula of each case only differs by the indexes. Therefore, we can calculate an analysis done case by case and get a general result. So this classification gives us a clear view of the Hessian matrix. And the formula at the bottom of this page shows how to derive the Hessian of the loss function based on the one-unit loss Cx. While I didn't put the explicit formula on my slide since it's too complicated, if you are interested in it, you may check our paper. Now, with the above derivation, we can verify some good properties of the Hessian. Let me introduce the assumption of bounded parameters. So we are restricting our optimization into a bounded domain, and hence we can use the mean value theorem to calculate the Lipschitz constant of auxiliary functions. This is the only assumption in our model, so it means that our result is of great probability. The mean value theorem for the vector functions are listed on this page, and we can directly call it to give a Lipschitz upper bound. Notice that the Hessian of the loss function can be expressed by the product of the auxiliary functions. Therefore, we introduce the following lemma to compute the Lipschitz efficiently. Basically, it says that the Lipschitz of the product of functions is bounded by a constant which is related to the number of functions, the maximum of the Lipschitz of each function, and the product of the infinity norms of the functions. This result can be proved by induction, and we use it to give the Lipschitz of the loss of the Hessian, which is shown on this slide. The Lipschitz constant has a polynomial bound given by the number of tokens n, the length of tokens d, and the radius of the domain r. And the next thing we verify is the lower PSD bound of the Hessian of loss, which is also a polynomial bound, and it can be derived by our assumption of bounded parameters. The result is shown on this lemma. Therefore, we can add a regularization term to the original problem, which makes the problem to be a strongly convex optimization with modulus L. So with these good properties, such as the Lipschitz continuity and PSD, we are able to apply a Hessian-based algorithm to solve our problem. The first thing of our algorithm is the introduction of a method given by Duan, Wu, and Zhou in 2022 that approximates matrices in the sense of PSD bounds. With this method, an approximation Newton method is provided. Basically, we use the approximation of Hessian in each update instead of directly computing the Hessian of the loss function, which is not efficient. This page states our main theorem, which says that if we assume the parameters are bounded and we take a initial point that is close enough to the optimal, then there exists a Hessian-based algorithm that approaches the optima in logarithm time. The proofs of the Lipschitz continuity and PSD can be found in our paper, and the convergence analysis of the Hessian-based method can be found in a paper by Li, Song, and Zhou. We omitted the formal proof in my presentation here since they are similar. In conclusion, our work provides an analysis framework on a large model-inspired regression, which studies the inverse recovery of training data via attention weights. We verify the existence of a convergent Hessian-based algorithm. Some future directions include enhancing the safety and effectiveness of large models. So our ultimate goal is to create a more secure and trustworthy environment for the deployment of transformer-based large language models. Here is the reference of my presentation, and thank you for listening.